Hello, this is Spencer Lyon, and in this video, we will continue studying networks and graphs, and will today learn about a concept called homophily. Before viewing this lecture, you should have already viewed the material on our introduction to graphs and networks, in addition to the content on strong versus weak ties in graphs. We will build upon these materials and concepts throughout our discussion in this video. Our main goals or outcomes for this lecture will be to understand the concept of homophily. We'll provide a definition of what this term means, as well as what it means within the context of graph theory. We'll then practice by working through some quote by hand examples of how we may diagnose the presence of homophily within a particular network. This will allow us to build up some intuitions behind what homophily is, when it's likely to exist, and how we can identify it. After building up our intuitions a little bit, we'll also learn some computational techniques that will allow us to diagnose homophily in a more repeatable and objective way, as well as a way where we can work with larger graphs that are difficult to analyze visually or without the aid of a computer. The key reference for the content today will be chapter 4 of the Easley and Kleinberg text, which again you can find for yourself by following the link here. The key packages we will use for our work today include Network X, which we import here using the canonical alias NX, as well as our old friend pandas. We'll also instruct matplotlib to put the figures directly in the notebook. So let's talk about the big picture, the main idea behind homophily. I want you to think for a moment about your family and friends, with whom you associate the most, and consider the following questions. Do they tend to enjoy the same movies, music, or hobbies as you? Do they hold similar religious or political beliefs? What about their background? Do they come from similar schools, workplaces, or socioeconomic settings? Consider these questions uh, within the context of your friends and family. After you've given that a little bit of thought, now I want you to consider the same set of questions, but this time consider that we just randomly sampled a handful of people from across the world. Now, and as you think about these questions, think about whether you believe it's likely that you'll hold similar beliefs uh, from people randomly sampled across the world, or if it's more likely that you hold similar religious or political beliefs with your close friends. Now, if you're like me, your answers will likely indicate that you have more in common with your friends than you would expect to have with some random subset of people. This is very natural. In some sense, the interests, beliefs, or preferences of individuals influence how networks are formed or edges are formed within a social network. Now, this concept, which we can summarize as we tend to be similar to our friends, is called homophily. It's not always the case that we'll be exactly the same along every dimension. That, quite frankly, would be pretty boring. However, the tendency to share preferences or beliefs or backgrounds amongst those with whom we have social connections, that tendency is stronger than sharing those type of backgrounds or beliefs with just a random subset of people. Now, let's think about this with a little bit more structure and within the context of a graph or a network. So, what we mean by homophily in a graph or network is that nodes that are directly connected to one another, meaning there's an edge that is formed between them, are, quote, more similar than nodes at a further distance in the graph. Now, the key term there that we'll need to define is what we mean by more similar. So here's an idea. We might have some friends in common. Consider a social network where we are represented by one node. We have some friends of ours who are connected to our node via edges. And our friends may have some common friends with us, in which case we would have a closed triangle among each group of three. But it's also likely that our friends know somebody else. So let's take a look at what this might look like. So suppose that this node right here represents me, and I may have some friends. And each of these friends, maybe some of them happen to know each other. And we'll say that these two know each other also. Now, each of my friends may also have friends. And sometimes they're going to know each other, but sometimes not. So, for example, this node out here is connected to my friend, but not to me. And as we've learned previously, the notion of triadic closure would suggest that it is likely that an edge might form between me and this other node out here. And it's even more likely that a node would form between me and that, or an edge would form between me and that node than, say, some other random node out here in its own component. Because we share this friend right here, we have this common link or background in that we both know this particular individual, means that it's more likely, under the property of triadic closure, that this purple edge will form than some edge that is connecting us, for example, this black one. Under triadic closure, this edge right here is less likely to form than the purple one. Now, we'll label this argument, the triadic closure argument, as an intrinsic force, meaning all of the analysis I've done with our little graph here has been using information explicitly contained within the graph itself. I made the argument that the purple edge is more likely to form than the black one using only the existing structure of nodes and edges defined in the network. This is what I mean by intrinsic. Now, an alternative way to think about this, about how nodes can be, quote, more similar, is to say that we may share some characteristics or properties that are not explicitly represented in the graph. And if you remember, the graph only represents nodes and edges. We can get some richness there by labeling edges as strong or weak, or even giving them a numerical value in the case of a weighted graph. But the only information the graph carries is what the nodes are and where the edges are. What the graph does not capture for us are any external forces or factors. Some common examples of external forces within a social network might include race, gender, which school we attend, who our employer is, what our favorite sports team is, etc. And if we're thinking about the similarity amongst nodes, we can definitely think about intrinsic similarities, meaning do we have edges between a common node? And then we can lean on things like triadic closure to determine how similar a pair of nodes is. But we think about the graph within its domain or within its context, there's likely a lot of external or extrinsic characteristics that could inform our analysis about which edges are likely to form or which edges may be stronger or weaker than others. Triadic closure is the key tool for helping us do this intrinsic analysis, and homophily, the concept as well as the definition, is what captures these external factors or forces. So, the quick summary here is we can think about nodes being similar either by the intrinsic properties of the graph or by extrinsic or external properties associated with each node, but not explicitly represented with the edges. An example of these external properties, it's maybe outside of the social network setting, would be suppose that you have a graph of manufacturing plants, and each of the nodes is a manufacturing plant or site, and each of the edges is would represent whether or not these nodes have any sort of inflow or outflow relationship. So, for example, you might consider one plant as harvesting raw materials and producing some necessary building blocks or intermediate outputs that would then be used by other manufacturing plants. Now, these ones further down the line may be responsible for collecting some intermediate outputs from these natural resource plants and assembling a final good for either business or individual consumption. Now, when you consider which nodes are linked, one obvious factor might be geography. And one way you might represent geography would be to capture the latitude and longitude coordinate for each node in the graph. Now, as we've seen in our visualization of various graphs, the node placement or position is typically random. It's not associated with the graph itself. So, this geographic information about where the plants are located would be external to the graph itself. It's not part of the list of nodes or the list of edges. However, when analyzing why one plant might be connected to another, taking into account geography and physical location may be crucial for really understanding or analyzing how or why edges have formed between particular nodes. Other examples of extrinsic properties within this context might be, do they belong to the same trade bloc or even the same country? And that might facilitate sharing of intermediate outputs because tariffs may be lower if you're buying intermediate goods from a producer within your same country. We may also consider other factors like the abundance of raw materials in one region, and then the co-location of plants that need intermediate goods that flow from those raw materials. So there are a whole universe of other properties that we might think of to get a bigger picture understanding of what's represented by this graph. Now, in order to identify whether or not homophily is active in a network, it's essential that we have additional context beyond the list of nodes and edges. Now, this is what we've been talking about as we think about these external characteristics. Now, as we're working in Python, one very common way to represent this context would be with a data frame in addition to a graph. And the way we will structure our data frame is we will say that the data frame has one row per node in the graph, and maybe one of the columns is maybe the node ID, so we can map between the data frame and the graph. So that's right here. And then we might have one column for each additional characteristic. If we're thinking about a social network, we may have the ID column as the name or username of the individual if we're thinking social media. And then the additional columns might include things like age, race, gender, home location, business you work at, schools you've attended, etc. So, as a quick and kind of contrived example here, consider the following data frame. We're going to construct this by hand from a dictionary, which has the following keys. The node ID column will list some names of individuals, and this is how we'll refer to each node within our graph. And then we'll have 5 different characteristic columns. One, we'll keep track of each person's favorite color. Then we'll keep track of the school they attended most recently, which sport they prefer to play, what their favorite food might be, and finally what their gender is. And this is entirely made up data. We have here my name, this is my wife and my oldest child, and then we have Michael Jordan and LeBron James, because we are obviously best friends. So let's go ahead and evaluate this data frame. And we have here additional context that we're going to use when we lay out a graph on the next slide. So the way we're going to construct our graph is we will use the networkx.graph class name. And as the only argument, what we'll pass is a list right here of edges that need to be formed. And the way the edges are going to be given to network X is with a tuple of 2 elements. Each element is the ID of a node, and the presence of these IDs within the same tuple means there needs to be an edge between the nodes. So here we have a total of 1, 2, 3, 4, 5, 6 edges, and they're formed between me and my wife, me and my daughter, me and LeBron, my wife and my daughter, my wife and MJ, and LeBron and MJ. So we'll go ahead and construct this graph and then just view it real quick so we can get a sense of what's going on. So we see here my daughter, she's only connected to me and my wife. I am connected to my wife, daughter, and LeBron. My wife is connected to me, my daughter, and Michael Jordan. And Michael Jordan and LeBron are also connected to one another. So we've been thinking and talking about this notion of homophily and how it means that edges are more likely to form between nodes that are similar along some external to the graph external dimension. Been pretty conceptual so far, but we're about to make it precise. And what we'll do is we'll kind of follow the statistics mindset, and we'll think about forming our idea of diagnosing homophily using the notion of a null hypothesis. So this concept should be familiar from our learnings of statistics, but it's not exactly the same because we're not imposing any distributional assumptions. And so we won't be able to give as precise statements or characterizations, but the idea that we'll propose that something is true and then test whether or not we can reject that proposal, that same workflow or mode of thinking will play out here. So the analytical work we're about to do begins with a thought experiment. So what we're going to assume is let's just think about a graph in which all the edges are actually randomly generated. There is no reason or rhyme behind why particular nodes are connected, and we'll just assume that all edges are random. Now, in this case, if all edges are random, the additional context we may have about nodes in our graph should not be helpful if we were trying to predict the structure or which edges have formed. We've just asserted that edges are random, and so if we happen to know the context or background behind our nodes, it shouldn't help us know where the edges are because they're random. So now let's consider a particular characteristic that we'll call x. This is going to be in our data frame before, this might be gender or favorite color. Thinking of one characteristic that we'll call x, and suppose that we have capital N nodes, and we'll say that n sub x of them exhibit feature x, and n minus n sub x of them do not. And we'll work with what we'll call them probabilities, but really we're counting frequencies. And we'll say that p sub x is equal to n sub x, the number of nodes that have characteristic x, divided by the total number of nodes. Now, if we will assert, and we probably need to rely on some law of large numbers here, but we'll assert that these frequencies that we've observed in our graph are probabilities of these characteristics occurring. And so we'll kind of sidestep uh, an intense discussion about what assumptions we're making here. And we'll just say that the frequencies are indeed, we can think of them like we do probability. Doing that, we will then say or be able to determine that the probability of an edge forming between two nodes that both share x is equal to px squared. So the probability that the first node we're thinking of has a feature x is equal to px, and then we're just going to multiply that by the probability that the other node has characteristic x, which is again px, and that's where the px squared comes from. Then we can say that the probability of an edge forming between two nodes that are both non-x types is going to be 1 minus px. And finally, the last probability that we'll consider is the probability of an edge forming between one node that has characteristic x and one node that doesn't. This probability would be either that the first node in our pair has characteristic x and the second doesn't, plus the probability that the first node does not and the second node does. These end up being the same term, and so the probability we're left with is 2 px times 1 minus px. Now, these probabilities or frequencies that we've just computed and described, this is going to be what we're going to call our random edge formation benchmark. So let's kind of put a pin in that, keep this in mind, and we'll come back to it here pretty soon. Now let's get kind of an empirical test value. So let there be a total of E edges in our network. And furthermore, we're going to attach a little bit more notation here. And we will say that E sub xx is the total number of edges between two nodes that both have property x in common. EYY would be the total number of edges between two nodes that do not have property x, and the E sub xy would be the total number of edges formed between a node that does have property x and a node that does not have property. And we'll see that these are exhaustive and mutually exclusive. So the identity here that allows us to decompose E into these three components: the two X node edges, the two not X edges, and the mixed X not X edges. Now, these four numbers we can compute if we're given a graph as well as the context around it. We can compute these numbers. And this will allow us to count the frequency of edges between the X and the non X types. So before, we were counting nodes. We were counting how many nodes had the property X versus total nodes. And that's what we use the N for. And now we're using our E notation to count the number of edges. At this point, now that we have our two summary statistics, we are ready to consider a test for the presence of homophily in a given network. To do this, we will consider the assumption or null hypothesis that there is no homophily in characteristic X. If this were true, what we would see is that the observed proportion of cross characteristic edges, meaning edges formed between one node of type X and one node of type not X, we'd see that the observed proportion of these edges is the same as the characteristic frequencies in the full population. More concretely, we would test this assumption by comparing our frequency of cross characteristic occurrences from just the node and context data in our data frame, which would be 2 times the probability of one node having type X and one node having type not X. And this represents again the likelihood or probability of a cross characteristic edge forming under the assumption of purely random edge formation. We want to compare that to the actual observed proportion of cross characteristic edges that we observe in our network. Now, when we compare these two numbers, we could get one of three outcomes. First, let's consider this middle row here. If these two statistics are about the same, that the actual observed frequency of cross characteristic edges is about what we'd expect if we just randomly sampled nodes uh, from our population. If that's true, we'd say that that null hypothesis holds, that there is no homophily. It doesn't seem that characteristic X is informative about whether or not an edge appears. Now, there's another case where this number, the actual observed edges, is going to be significantly less than what we would have expected under our hypothesis of no homophily. In this case, we would reject that hypothesis and we would say that there is evidence of homophily. Because if you remember, this E down here is the total number of edges. And so if the proportion of these edges that exist are for cross characteristic matches is really small, what must be true is that the proportion of EXX or EYY matches must be relatively larger. And in this case, that's exactly homophily, saying that two nodes of either type X or two nodes of type not X must be more likely to have an edge formed than nodes of one X and one not X. So if this is significantly smaller, the observed rather than the expected, we say that there is evidence for homophily. And the final case is if this is significantly greater. So if this proportion of edges that are cross characteristic is much larger than what we would have expected, we'll say that there's inverse homophily. And we'll talk about this here really soon. We'll have an example of it. The intuition behind this test is that if this observed cross-characteristic edge formation is significantly less than what we would have thought or expected if we just randomly drew edges, then we would reject that hypothesis that there's no homophily, and we'd be left to conclude that characteristic X is meaningful when we consider edge formation. So let's see, let's work through a quick example. So suppose we have a network, and right now I'm just going to write down some of these key numbers. I'm not going to draw the whole network out. So suppose that there are a total of 18 edges in our network, and we'll say that EXY, the number of cross-characteristic edges, are 5. And for context, we're following an example from section 4.1 of the Easley-Kleinberg text. And the graph that they think about is elementary school kids and whether or not boys and girls are friends. So the graph has a total of 18 friend relationships mapped out. And of those 18, only 5 of them are between boy girl pairs. Now, we'll also say that n is equal to 9 in this example. And we'll say that x, characteristic x would be male and y would be not male or female. And we'll say that nx, the number of individuals who are male in our example. Now, let's say that the number of male individuals is 3 and the number of female individuals is 6. So now let's compute our numbers. So we have p of x is equal to 3 over 9. We have 1 minus px is equal to 6 over 9. And so this expected probability under random edge formation would be 2 times 3 ninths times 6 ninths. And here, what this ends up equaling is 8 out of 18. Then let's consider what we get when we consider the observed edges. So here we would have 5 over 18. And so in our case, we would say that 5 over 18, I'd say that that's less than 8 over 18. And so in this particular example, we end up in this bottom row. I'd say that the difference is significant here. And so we say that in this example of friendships forming in elementary school kids, there does seem to be evidence for homophily. If you sample 2 random individuals, if both of them are male or both of them are female, it's more likely that they become friends than had you sampled 1 male and 1 female. So let's think of another example. Recall the graph of romantic relationships amongst high school students. And now our question is, does this graph exhibit the characteristic, or does this graph exhibit homophily in the characteristic of gender? So if we look carefully here at this graph, we see, I'd say that roughly half of these individuals are male, given that they're blue dots, and then half are female. So if we say that, I don't know what n or nx is, but we can say that px is roughly a half. And so what we would expect, we would consider 2px times 1 minus px is equal to 2 times a half, which is equal to just 1/2. So that is the proportion of cross-gender matches we would expect to see if there was no homophily active. Now, just kind of eyeballing this graph here, it looks like almost all of these edges are going to be cross matches. I see one example here of two females, but other than that, I don't really can't identify any other same gender matches. So suppose in this graph, we'll just make up a number that E is approximately 200. And now we're going to say that EXY, the number of these edges, from what I can tell visually, is equal to 199, because I only found one example of a same gender match. So now we have 199 over 200. And we're going to say that this is significantly greater than 1/2. And in this case, we're going to be at the top row of that table before, where we would say that this particular network exhibits strong inverse homophily. And the idea there is that when you're looking at the characteristic of gender, it is much more likely that an edge would form between edge nodes with different type of gender than nodes that form between the same type of gender. That's what inverse homophily would mean. And that seems to be the case for this particular network. There's strong inverse homophily in the gender characteristic for this particular graph of high school students. And so this was purely an empirical statement based on the graph or the network that we're seeing here. And we would say that there is evidence of inverse homophily in the gender dimension. So now let's go back to our made up data where we had some members of my family, as well as some NBA stars. And if you remember, this was our graph. We have here me, my wife, my daughter, and then Michael Jordan and LeBron James. And here there's kind of a structure for how these nodes are, what the graph looks like. And then we have here a number of different characteristics. We have their favorite sport, school, color, food, and gender. So in order to test for the presence of homophily under any of these particular dimensions, what we need to do is first count the frequencies for each of our characteristics. So in order to count the frequencies, we'll actually use a helpful class here from the built-in collections module in Python. And so we'll import the counter type from this module, and we'll define one function. So here we have a function called count frequencies, and we'll go ahead and say that this accepts arguments of a list. And then the first thing we'll do is we'll send our list of values into the counter type. And what it's going to do under the hood is it will iterate through the list one item at a time and keep track of how many times each item appears. Then we're going to just ask for what's the total number of items in our list. So this would be kind of like n. And then this one would be kind of like n sub x for all x that appear in vals. And now our return value is going to be equal to nx over n. What we'll do is this we can kind of treat as if it were a dictionary. We can ask this counts object to iterate over its items. When we do that, it will give us back key value pairs where the key or the first element is whatever item appeared in our list vals, and the associated value, v, will be the number of times that appeared. So then we're going to associate each value with the number of times that appears over the total number of nodes. We're going to be computing exactly that nx divided by n. So we'll go ahead and we will count our frequencies. And if we pass in the gender column, we'll see that 60%, or in this case, 3 out of 5 of our edges had the gender male, and 2 out of 5 has gender female. So this function seems to be working. And now what we'll do is we will construct a dictionary now that maps from a column name to the values here will be another dictionary of the frequency. So let's check this out. So here we say, if we look at the node ID column, well, each of these is unique. So there's probability 0.2 for each name. But then we have the probability if we just randomly sampled 2 nodes that it would be, if we were going to sample a single node, the probability of the favorite color would be 40% blue, 40% pink, 20% red, and so on. So we have here all of our p sub x values that we need for our computation. Now that we've counted frequencies, we need to be able to count our edges. So first what we'll need, if you remember the key numbers that we needed on this one, we needed E, which would be the total number of edges. This one's pretty easy. We can just get that directly from network X. And then we also need EXY, which would be the number of edges between X and not X. So this step is a little bit trickier than what we just did because it's going to require that we access data from both the graph and the data frame at the same time. And to not spoil the fun, we're actually going to leave this as an exercise that we'll come back to later on, and either as homework or just later on in this notebook. And for now, we'll just look at how we might do this by hand. So let's look at the favorite color column, and let's consider whether or not edges are likely to form between people based on their favorite color being blue. So there's a total of 6 edges. This is E. Of those 6, 5 of them are going to be cross characteristic, meaning 5 of the 6 edges are between people with different favorite color. So the ratio of cross edges is 5/6. The ratio of blue nodes is 2/5. And so now we'll do our test here. So what we'll see is we have our E, how we're going to compute it from the graph. We counted the number of edges that were crossed. We have the number of blue nodes, the total number of nodes. We have px. And finally, we'll do our test. 2 times px times 1 minus px, and then exy over e. And what we'll see is that we have the 2 times px times 1 minus px term equal to 0.48. Which is equal to 2 times 0.4 times 0.6. And then we have here 5/6 or 0.833. So now what we have is we have a significant deviation here, and the observed frequency of cross characteristic matches is much higher than the expected. And in this case, we have an instance of inverse homophily, which we summarize as opposites attract. This is similar to the gender formation or edge formation in that high school relationships graph. So we have here an exercise we suggest that you work through where we want you to repeat the counting exercise, but a different characteristic. Consider gender or favorite sports. And as bonus, it would be great if you would be able to write a Python function that would allow you to pass a data frame, graph, and a column name, and be able to return those 2 statistics, the expected frequency of cross-characteristic edges based just on the counts of characteristics, as well as the observed using the edge data. So in particular, what we would be asking for is a function like this, the test homophily, where we could have a graph, data frame, and a column. What this would do would be to test for homophily in the graph based on df column. Returns 2px times 1 minus px and e xy over e. So this would be the ideal way to kind of solve this problem, is if you come up with a Python function that uses the graph as well as the data frame together to analyze homophily in a particular column. So this will be the end of this video and the end of our introduction to homophily. We'll see you next time, where we consider further properties of graphs and further our knowledge of how we can analyze